Now, moment of a couple. By definition, two forces forms a couple if they verify the following conditions: non-collinear, same line of action, same magnitude, and opposite direction. By observing this figure, we show that F1 and F2 are two forces represented on it. If we consider an axis of rotation delta passing through the point O and perpendicular to the plane of this figure, and we consider this solid of irregular form, for example. In this case, F1 and F2 have same line of action or parallel line of action. So the line of action of F1 is parallel to that of F2, and F1 and F2 are non-collinear, and F1 and F2 are represented by two vectors of equal length, so the magnitude of F1 equal to the magnitude of F2, but F1 and F2 are in opposite direction. In this case, F1 and F2 forms a couple. So the conditions of a couple are: the two forces should be non-collinear, same line of action, same magnitude, and opposite direction. The moment of a couple, in this case, we prove that the moment does not depend on the position of the perpendicular axis to the plane of couple. This moment is equal to the product of common magnitude of two forces, since in conditions the two forces should be of same magnitude. So F1 equal F2 equal simply F. So the moment of couple in this case is calculated by the product of the common magnitude F by the distance separating the two forces, or the distance separating the two lines of action relative to F1 and F2. And in this case, the moment of the couple does not depend on the position of the perpendicular axis of to the plane of couple, or does not depend on the axis of rotation, the position of axis of rotation delta. So the moment of a couple has a certain conditions, that the force does not or the force should be non-collinear, same line of action, same magnitude, and opposite direction. Now, equilibrium of a body. A body is in equilibrium or in total equilibrium if the two following conditions are satisfied. In first situation, a body is in translational equilibrium if the sum of external forces acting on it is equal to 0. And in second situation, a body is in rotational equilibrium if the sum of the moment of external forces with respect to an axis of rotation delta equal to 0. If the two conditions are satisfied for a body, so in this case, this body is considered in total equilibrium or simply in equilibrium. Application. The figures below, or the figure below, represents a vertical cross-section of systems at, or of system at equilibrium, given, if possible, gravity equal to 10 Newton per kilogram. So in this figure we have a rod, a homogeneous rod AB, a homogeneous rod, so the distribution of mass is uniform. So if we cut, for example, the rod in two parts, we have two parts of equal mass. So in this case the rod is homogeneous. So AB is a homogeneous rod of mass 40 gram, of length AB equal 30 centimeter, AO equal 10 centimeter. Question: calculate M2, the mass of solid represented in this position. We have to calculate its mass. So calculate M2 and determine the line of action and the magnitude of the reaction of the support at O. So we have to calculate in this question the value of M2 and to determine the line of action and the magnitude of the reaction of support at O. This is the support and this is the rod AB. At O we have a reaction. We have to calculate its line, to find its line of action and its magnitude. Solution. If we consider, or if we return to the given, it's important to take in consideration that the system formed on the rod AB and the masses M1 and M2 is in equilibrium. So since it is in equilibrium, we can apply the conditions of equilibrium of this body in translational and in rotational case. In first situation, the forces acting on the rod AB are its mass, its weight, M times G, the tension at A, where the tension is equal to the weight of M1, the tension T2, for example, at B, where it's equal to the weight of M2, and the reaction of support at O. So the rod AB undergoes the action of four forces: weight 1 applying at A, weight 2 acting on B, the weight of the rod represented at its center of gravity, and the reaction of support represented at O. So we have to calculate the moment of these forces if we are going to apply the rotational equilibrium. So the forces acting on the rod: weight of M1, weight of M2, weight of the rod, and the reaction of support at O. In first situation, since the rod is in equilibrium, so it is in translational equilibrium and in rotational equilibrium. So the rod is in rotational equilibrium around O. So sum of moment of all forces or all external forces acting on the rod should be equal to 0 according to the principle of rotational equilibrium. Sum of moment of external forces equal to 0. So the moment of weight of M1 plus the moment of that of M2 plus the moment of the weight of the rod plus the moment of the reaction of support, the sum of these four moments should be equal to 0. The moment of the weight M1, this is the positive direction chosen. If we consider that the weight of M1 only acts on the rod, when we apply this weight at A, we show that the rod rotates in this direction, so in positive direction. So the moment of W1 should be positive and equal to the magnitude of the weight times the lever arm. So times the distance OA, since the lever arm is found when we trace a perpendicular issued from the axis of rotation O to the line of action of the force. So this perpendicular is shown or is represented by the distance OA. The moment of force relative to W2 is the magnitude of W2 M2 times G times the distance separating the line of action to the axis of rotation. So if we draw the perpendicular issued from O to the line of action, this is the line of action is vertical, and the perpendicular drawing from O to this line of action is the distance OB. And if we consider that W2 only acts on the rod at B, we show that, or we notice that the rod rotates in this direction, so in opposite direction or in negative direction. So the moment of the force W2 should be negative and has a magnitude minus, or a value minus M2G, so it's the magnitude of the weight times the lever arm OB, that equal the distance AB minus the distance AO, equal to 20 centimeters. And if we are going to calculate the moment of the force of the weight of the rod, similarly, this is the line of action, and from O we draw the perpendicular. We find that the lever arm relative to the weight of the rod is the distance OJ. So, and if we consider that the weight of the rod only acts on the rod at J, we notice that the rod rotates in this direction, so in negative direction, so its moment should be negative and equal minus M the rod times G times the distance or G. The line of action of the reaction of support cuts the axis of rotation, so R has no moment, or the moment of the reaction of support is equal to 0. Finally, if we replace all moment calculated in this part in this equation, we find that M1G times OA minus M2G times OB minus MG times OG plus 0, this is the moment of the reaction of support, is equal to 0. In this equation, we have only M2 unknown. So all parameters in this equation are known, but only M2 is unknown. So we calculate M2 equal, and we find its value equal to 40 grams. In second situation, we have to determine the line of action and the magnitude of the reaction of support. When we apply the rotational equilibrium, we find that the moment of R is equal to 0. So in this case, when we apply the rotational equilibrium, it's impossible to find the line of action of R and its value. Knowing that the moment of R is equal to 0, and this does not mean that R equal to 0. It's important to notice that the moment of R is equal to 0, but R, or the magnitude of R, does not equal to 0, and we are going to find it by applying the translational equilibrium, that is equal to, or defined by, sum of external forces acting on the rod should be equal to 0. So the external forces are the same. The weight of solid M1 plus the weight of solid M2 plus the weight of the rod plus the reaction of support. All the summation or the sum of these forces are equal to 0 according to the translational equilibrium. The weight relative to M1 and M2 and the rod are vertical. Hence, the line of action of R is vertical. So, according to this relation, since M1G, M2G, and Mg, these three vectors or these three forces are vertical, so it's necessarily that the line of action of R is vertical. By projection this relation on a vertical upward axis, if we return to the figure, if we consider an axis vertical and, for example, similar to y prime y in an orthonormal system, if we make projection of all forces vertically upward, we find that all weights in this relation are vertical but in opposite direction, since all weights are represented downward. So by projection we obtain minus M1G minus M2G minus M rod times G, but only R is vertically and upward, so R only it is represented in positive direction of the y prime y. So minus W1 minus W2 minus W of the rod, so the weight of the rod, plus R is equal to 0. So by calculation we find that R equal M1 plus M2 plus M times G, and if we replace M1, M2, M and G by their values, we obtain finally R equal to 1.8 Newton. Now, how we apply Newton's second law in rotation. By definition, Newton's second law in rotation is defined by the sum of moment of external forces equal to I times zeta double prime. If we have a solid that is this solid does not in rotational equilibrium, so the sum of the moment of external forces does not equal to 0, so it's equal to a certain quantity. By definition, this quantity is equal to I, the moment of inertia of the solid, times its angular acceleration zeta double prime. Application. The adjacent figure shows a solid homogeneous sphere of mass m equal 2050 gram and of radius r equal 10 centimeter, moving around a vertical axis delta. So in this figure we have a sphere that it rotates around a fixed axis delta passing through its center. A string is wounded about the great circle perpendicular to the axis delta of the sphere and pulled with a horizontal constant force F of magnitude F equal 4 Newton. So this is the string wounded about the great circle, so around the sphere, and the force coming from this string has a line of action perpendicular to the axis of rotation delta passing in the center or at the center of the sphere. Knowing that the moment of inertia of the sphere with respect to axis of rotation delta is I equal 2 over 5 mass of the sphere times its radius square. Question. Study the moment of rotation of the sphere in the absence of the force of friction. So we have to study the moment of rotation or the motion of rotation of the sphere in the absence of the force of friction. So we are going to determine the nature of the rotational motion of the sphere and we take in consideration that this rotation takes place without friction. Solution. The sphere is under, so since from the given, the sphere, or it's clear that the sphere is not in equilibrium of rotation, or in rotational equilibrium. So we are going to apply Newton's second law to study its motion and deduce its nature. So the sphere is under the action of its weight, the reaction of the axis of rotation R, and the force F coming from the string. By applying Newton's second law for rotation, the sum of moment of external forces with respect to the axis delta equal the moment of inertia I times the angular acceleration theta double prime. We find moment of the weight plus moment of reaction of support plus moment of the force of the string equal I times theta double prime. Moment of the weight of the sphere, this is the weight vertically downward, so the weight is, or the line of action of the weight cuts the axis of rotation, so its moment is equal to 0. And the reaction of support, or the reaction coming from the axis of rotation on the sphere, also the reaction of this axis has no moment, since its lever arm, or its distance with respect to the axis, is equal to 0. So finally, the moment of the weight and reaction of axis are null, since the weight, its line of action parallel to the axis of rotation, and it's confound with it, and the moment of reaction is equal to 0, since R cuts the axis of rotation delta. So we have to calculate only the moment of the force coming from the string equal to I times theta double prime. Returning to the figure, this force is tangent to the sphere. So if we are going to determine the lever arm relative to this force, we find that the distance separating the axis of rotation and the line of action of the force is equal exactly to the radius of this sphere. And if we take in consideration the positive direction of rotation, that this in this direction, in same direction of the force F, we find that the moment of the force is equal to plus times the magnitude of F times the radius R of the sphere equal to I for the sphere times its angular acceleration. We replace I by its expression, and we can simplify by R and the square. We find finally the angular acceleration equal to 400 radian per second square, which theta double prime is a positive constant, so the motion of the sphere is uniformly accelerated. So the sphere describes a circular or a uniformly accelerated motion. Now we are going to show an application concerning or relative to moment of a couple. If we consider a homogeneous rod AB of length L and mass M can rotate in a horizontal plane around a vertical axis passing through its midpoint O. So we consider this rod AB, and delta is the axis of rotation passing through the center O of the rod AB. And F1 and F2, a couple of forces F1 and F2 is applied perpendicularly in the horizontal plane of the rod at its edges A and B. The two forces have a constant magnitude. In this given, it's clear that F1 and F2 by given forms a couple. So it's necessarily that F1 and F2 satisfy the conditions of couple. If we need, or if we are going to verify that in fact F1 and F2 represent or forms a couple or no. In first situation, F1 and F2 are, or the lines of action of two forces are parallel, and F1 and F2 are non-collinear. F1 and F2 by definition have constant magnitude and same magnitude, and F1 and F2 are in opposite direction as shown in this figure. So it is so F1 and F2 forms a couple. Question: show that the motion of rotation of the rod is uniformly accelerated. So we have to verify that the motion of rotation of the rod is uniformly accelerated. In this case, we are going to apply the Newton's second law in rotation, since we have to study a motion of rotation. So we apply the Newton's second law in rotation. The sum of moment of external forces equal to I times the angular acceleration. The external forces acting on the rod are F1, F2, or the couple formed by F1 and F2, its weight, and the reaction of X. Since the weight has a line of action parallel to the axis, so the moment of the weight is equal to 0. And since the moment or the reaction of axis has a line of action cutting the axis, so also the moment of force or the moment of reaction of axis is equal to 0. So we have to calculate only the moment of the couple formed by F1 and F2, and by definition we know that the moment of a couple is or does not depend on the position of the axis, but the moment of a couple is equal to the product between the common magnitude and the distance separating two lines of action of two forces. So the moment of couple is equal to the common magnitude F times L, where L is the length of the rod, since F1 and F2 are applying or are applied on the rod perpendicularly, F1 at A and F2 at B. So by applying Newton's second law, we find that F times L equal I times theta double prime, and theta double prime, or the angular acceleration, equal FL over I, where I equal I of the rod by given 1 over 12 times the mass of the rod times its length square. We find that the angular acceleration equal 12F over m times L equal to a positive constant, since F, m and L are positive. So the acceleration equal to a positive constant, so the motion of rotation of the rod is uniformly accelerated. And thank you for your observation.